The Gemini training program of Innovative IDM presents Sensors, an overview of functionality and application for industrial automation. Hi, my name is Nick O'Connor. Sensors are as prevalent in the industrial automation environment as any other component. The need for sensors is not lost on anyone who works in the field, as sensor output is imperative for the successful execution of most systems. Though sensors are a common component, the many types of sensors are as diverse as the many applications that they can be used for. In this video, we will discuss how different types of sensors operate, how sensor size affects range and mounting, some common applications that utilize these sensors, and finally, we'll finish with a demo that showcases the precision of fiber optic sensors. Let's take a closer look. Welcome back. What I have laid out here are various sizes and models of photoelectric sensors. Photoelectric sensors are widely used due to their versatility and their ability to detect both metallic and non-metallic objects. Photoelectric sensors operate using light. Generally speaking, a photoelectric sensor will have an emitter that sends out light and a receiver, which is there to detect the amount of light that is reflected back. There are three basic types of photoelectric sensors: a through beam sensor, a retroreflective sensor, and a diffuse reflective sensor. Each one has different operating principles. However, they all use light to either detect the presence or absence of an object. In the past, Innovative IDM has filmed a video specifically designed to teach you guys about the differences between these types of photoelectric sensors. If you're interested in learning more about those, we'll leave a link to that video in the description below. However, for those of us that have a working knowledge of these sensors, let's move on and see how the different sizes may have a benefit for your application. What I have here is an 18mm threaded photoelectric sensor. This sensor is a favorite of many due to the ease of installation and the ability to adjust the sensor after it's been installed. To mount a sensor like this, simply drill a hole, insert the sensor, and tighten the nuts down to the appropriate height and orientation. Why people love these sensors is that you have the ability to adjust the height of the sensor and the sensing direction with ease. Though threaded sensors are popular and solve a wide variety of problems, oftentimes their use is limited due to their bulky size and the reliance on drilled holes to mount. Now, let's imagine we have an application where we're going to use a photoelectric sensor to sense objects running down a narrow conveyor. Now, we don't have the ability to drill holes to mount a sensor, and we also can't afford to have a sensor protruding out into the conveyor lane. What we might use is a similar photoelectric sensor that's very small and very flat. A sensor like this can be mounted up into the side panels or the railings of your conveyor, and it can be able to sense objects without the hassle of a protruding sensor. Though photoelectric sensors are versatile, they are susceptible to variations in accuracy due to a variety of factors, such as changes in ambient lighting or dust. In a situation in which we'll be sensing a metal object, it might be advantageous to use an inductive proximity sensor, which uses the properties of eddy currents to detect the presence or absence of a ferrous part. Inductive proximity sensors are not affected by dirt or grime and are thus the sensors of choice to be used in messy environments. Innovative IDM's own Adam Ring has gone into depth into the difference between inductive and capacitive proximity sensors and how they use eddy currents and the properties of magnetism and electricity to sense objects. If you'd like to learn more about these proximity sensors, we'll leave a link to that video in the description below. But for now, we're going to focus the rest of our talk on proximity sensors to the difference between a shielded and an unshielded inductive proximity sensor. What I have here are a shielded and an unshielded inductive proximity sensor. You can easily tell the difference between the two because a shielded proximity sensor will have metal threads that run the entire length of the body, while an unshielded version does not. Now, what you need to know is when and where you will use either one of these options. An unshielded inductive proximity sensor is going to have a greater sensing distance than its shielded twin. Now, a greater sensing distance might be beneficial to you in your application, but however, because of the way that these sensors are mounted, an unshielded version might not be the best thing for you. In order to mount one of these sensors, you normally will drill and tap a hole into a piece of metal and then thread the sensor up until the distance that you need. However, an unshielded version is going to be able to sense on top of the sensing head as well as around it. This brings in some obvious problems. If you take an unshielded inductive proximity sensor and screw it in flush to a metal surface, it will always give an output, as it will always sense the metal that it's housed in. In this case, an unshielded proximity sensor is not embeddable. On the other hand, a shielded proximity sensor might not have the same sensing distance pound for pound, but what it lacks in distance, it'll make up for in recessibility. A shielded proximity sensor can only sense on top of the sensing head. It has no sensing ability out to the sides. This being said, when a hole is drilled and tapped, you can screw this sensor in right up to the level. This gives the opportunity for objects to either pass directly over the top of the sensor, or maybe even directly in front, without impeding the movability of the objects. It all depends on your application and if you need to have space or not. Now, let's take a closer look at an Omron fiber optic sensor and its accompanying amplifying unit. Fiber optic sensors are especially useful for applications in which you might expect to experience electrical noise in your lines. The reason that they're useful is because fiber optic cables do not have any electrical components. Thus, they're impervious to electrical noise. In a real-world application, the fiber optic cables will be run from the sensing object over to an external amplifying unit. The amplifying unit will house both the emitter and the receiver, as well as the brains for the sensor. An amplifying unit, like this Omron E3X HD, houses both the emitter, the receiver, and the brains for the fiber optic sensor. You can see that as I pass power to the amplifying unit, red LED light is distributed from the emitter. In a real-world application, a fiber optic cable would be attached to the emitter, which would run down to the sensing head and then back through a separate fiber optic cable to the receiver. The amplifying unit will then take into consideration the amount of light that it received and fire an output based on thresholds that you, the user, have set. Now, these amplifying units are designed to be mounted to a piece of DIN rail, and thus are able to be stored in your control panel with all of your other control equipment, safely away from the harmful effects of electrical noise. To showcase the ability and the precision of this tiny fiber optic sensor, we've arranged a demo to differentiate between the amount of reflected light off of a folded sheet of paper. Now, the thickness of a sheet of paper is about 0.1 millimeters, or 1/250th of an inch. So, as I fold the paper over, I create a tiny step, and that step, because it's higher, should reflect more light back to the fiber optic sensor. So using the amplifying unit, I have trained the sensor to know that right now it's receiving a certain amount of light from the bottom step. However, as I move the paper over and it steps up to the folded sheet of paper, the sensor is going to receive more reflective light and thus fire an output. Let's give it a go. You hear that? So because the paper is higher and closer to the sensor, we're going to read a higher intensity of reflected light. So as I move the paper back and forth, even though it's just a difference of 0.1 millimeters, this sensor still has the power to discern. It's pretty cool. On behalf of Innovative IDM, we'd like to thank you for stopping by our channel today and checking out our video about different types of sensors and some of their benefits and the applications that you might find them in. For more information about these types of sensors and any other piece of industrial automation equipment, please give us a call or check out our website at innovativeidm.com. Until then, we'll see you next time.